Hey guys, so these are your 10.4 notes, and we're going to be bringing in the unit circle and some basic geometry talking about the rectangular coordinate plane, so that's your xy coordinate plane. So the first thing I'm going to do is I'm going to put on my circle the unit circle points. Just in radians. So go ahead and take a second, do that on your own. So if you're looking for a way to memorize the unit circle, the denominators are always going to be 6, 4, 3, 3, 4, 6, 6, 4, 3, 3, 4, 6. And then the numerators are always going to have pi. And then the number within the numerator is going to always be a 1 in the first quadrant. In the second quadrant, they're always 1 less. So 3 has a 2, 4, 3, 6, 5. And the third quadrant, it's always 1 more, 7, 6, 5, 4, 4, 3. And then I just remember 5, 7, 11. And then as far as, I'm only going 90 degrees, so it's like a half, 1, 1.5, 2. Okay, so just a quick review on the unit circle. So the polar coordinate plane is a different way to plot points. When I taught at ITT Tech, I actually had a student that at one point took like pilot classes or something. He flew planes, and he said, when I taught them this unit, that it really reminded him of radar. So I think if you're just traveling along something that's not a nice straight line, or if you're traveling on a curve, I'm sure there's connections with the orbit, and like I said, maybe flying. So it's just a different way to plot a point, but there are a lot of similarities. So that's what we're going to be looking into, are these polar coordinates. This should be brand new. I don't think you've seen this any other time. And so right now, this point is about at 4 pi over 4. So we're talking about more like angles instead of just over x up y. We're looking at something at an angle here. So let's talk real quick about some quick pre-calc review. And if I'm talking about the coordinate point 4 pi over 4, what are some other ways I could write that exact same coordinate point? I'm going to kind of scroll back up here so you can see a little bit of my picture. So one thing you could do is you could think about coterminal angles. So if you're starting at pi over 4, you could loop back around in either direction. So if you add 2 pi or subtract 2 pi, that will give you 2 more answers. So if I take pi over 4 and add 2 pi, that's 9 pi over 4. If I take pi over 4 and subtract 2 pi, I'll get negative 7 pi over 4. Some other things to think about is maybe where you could start in a different place but still end up at the same point. So if you think about like a reflection, okay, you could start here at negative 4 because we're going to the left, and instead go negative 3 pi over 4, or you could go 5 pi over 4. Okay, so the distance from here, you can go either this way or that way. So these are the same exact coordinate points. Well, not the same coordinate point, but it's going to get you in the same place. So just think about things like that. A little review from pre-calc, okay? We're also going to talk about how this connects to the rectangular coordinate plane, which you're already familiar with. So if I have an angle pi over 4, which is 45 degrees, and my radius is 4, that's what's indicated here. You got your r and your theta, so radius is 4. And this is my x, this is my y. Well, what's cosine pi over 4? That would be x over 4, adjacent over hypotenuse. Sine would be y over 4. And so if you could rewrite that, you can multiply both sides by 4. You would get x equals 4 cosine pi over 4. Likewise, you could do that for y, or sine pi over 4. Now, we could actually work each of those out because we know pi over 4 is radical 2 over 2. So if you substitute that in for each of these, what would you get? 2 radical 2 for each of those. So what I'm saying is, if you look at the coordinate plane, and here we're saying our radius is 4, our angle is 45 degrees, or pi over 4. If I would plot that point in the coordinate polar plane, then I need to have that information, radius and angle. But in the rectangular coordinate plane, I could simply go over 2 radical 2, up 2 radical 2. So it's 2 different ways to get the same result. It just depends on what kind of situation you have. Okay, so here are your formulas, and really these, we just kind of already formulated these, so when you're looking at your angle theta, and here's your r, your x, and your y, you know, I know that cosine is adjacent over hypotenuse, and I know sine is opposite over hypotenuse. If you just kind of rework that solving for x and y, that's how these come about. So you really don't need to memorize them because they can easily be found. And you could also find tangent, which would be y over x, and that'll come in handy later on. And that information is also over here, so if you want to find an angle, you can do the inverse of y over x, so a little bit of geometry and trig coming into play there. And then likewise, if I want to find r, it's just Pythagorean theorem, x squared plus y squared equals r squared. So if I wanted to, you know, if I take the square root on both sides, I'm going to get this. So you have a lot of formulas here that you'll need to memorize, but you can really, you don't have to focus on memorizing them because they're easy to just derive yourself. All right, so let's look at some examples. First one, I've got an r and I've got a theta, and I want to find the rectangular coordinates. Well, we have these formulas where I can find x and y. X is 2 cosine 5 pi over 6. Y is 2 sine 5 pi over 6. Okay, if you're a little rusty on the unit circle, it's about to start coming back to you. If you don't know it, you may want to look it up and jot one down. So I'm going to substitute in what 5 pi over 6's value is for cosine and for sine, and just kind of clean those up a little bit. And that's going to give me my xy coordinate plane. Not coordinate plane, but my rectangular coordinate point. Okay, so if I plotted this on the polar, it would be the exact same position as this. Okay, this time I'm going to go backwards. I'm going to start with an xy, and I'm going to find my r and my theta. Well, your r is just Pythagorean theorem, so I'm going to square each of these. 9 and 9, that's 18. You can simplify that to be 3 radical 2. Theta, we need to find an angle. You could use sine or cosine or tangent. I normally like to use tangent, especially in cases like this, where it's negative 3 over 3, because that's the inverse tangent of negative 1, and I know that that's going to be that pi over 4 family. Now, it's not exactly, it could be a pi over 4, because that's where it's positive 1, so it has to either be in this quadrant or in this one. Now, I'm going to pick 7 pi over 4, because that's down here, and if you look at where the other coordinate point is, your radius is positive, so that means I have to be on this side, okay? If this was negative, which it shouldn't be, then I could be on the other side. Now, could I easily tweak this like we did in the beginning? Sure. So here's my answer. There's my, erase that, my radius, and my angle. Okay, so like I said, if you wanted to change this and make it a negative, then you could change this angle. But why do all that when you get the answer from that point? Okay, so what we're going to do here is we're going to do a little bit of algebra, and we're going to convert the following from polar to rectangular. So what you have to, from rectangular to polar. So what you have to do is recognize that y is r sine theta, and that x is r cosine theta. Okay, and you could really just leave it like that. Pretty simple. Same thing here. Y is r sine theta. Done. And this one, I can say that, well, if you recognize what this is, x squared plus y squared, that's going to be, that's your r squared, because we know r is the square root of x squared and y squared. So if you square both sides, that's going to give you r squared equals 16. And you can easily solve from r from there for any of these. Okay, you can just leave it like that. Now we're going to go from polar to rectangular, so we're going to work backwards. So what you have to do is recognize that something is missing here. Okay, so you got that r cosine theta that we know is x. It's not there, so what I'm going to do is manipulate this so that it looks more like a polar coordinate, polar coordinate point. Okay, try saying that 5 times fast. Now I can actually substitute in what r squared is, and that's just going to be x squared plus y squared. And I know that this is x. And if you want to get, y by itself, you could easily do that. You don't have to, either way. But if it's multiple choice, you want to make sure that you're able to match it up with the right answer. Okay? But if it's free response, you can just leave it. All right, so this one, you've got theta, and we need to figure out what tangent of 3 pi over 4 is. So if you look on the unit circle, that's one of your 45s. That's going to be the one that's negative. So we know tangent is y over x. So I'm just writing the word tangent on both sides is what's happening. So I'm just doing algebra, whatever I do to one side, I do to the other. Tangent theta is y over x. This value is -1. And you're done, okay? Because if you multiply both sides by x, this is what you get. All right, so now I've got r is cosecant theta. Well, we haven't talked about cosecant, but hopefully you remember from pre-calc that cosecant is 1 over sine. And so I can kind of clean this up a little bit by multiplying both sides by sine. Point of that is I know that r sine theta is 1. All right, so you're just kind of playing around, a little bit of algebra. The next thing we're going to do is slope of a polar equation. So we already talked about slope before in the last section, and we were talking about dt's a lot of times. Same kind of thing. So you got dy over d theta, dx over d theta. You're going to be doing a lot of product rule. Okay, so however you write that, that's what's going to happen here for your slope. And same thing as before, whenever we would find... Okay, so I'm going to go ahead and start another video because I can only record for 15 minutes and for the next set of problems. Okay, so